Hello students, today I will take here the topic of the electrical properties of the MOS circuits. So MOS is basically the metal oxide semiconductor circuits. So MOS basically I have discussed here the basically in VLSI where electrical current and voltages are the most important quantities. So MOS conduct electrical current by using an applied voltage to charge from the source side to the drain side of the device. So since the basically the drain and source are physically separated, the flow of the charge underneath the gate can occur only if a conductor path or the channel has been created between the drain and source. So most important basically I will discuss here in this basically topic here the basically the controlling voltage, because the working of this controlled by the capacitively coupled field acting field which is acting perpendicular to the semiconductor surface. So in MOSFET is basically it is also named as insulated gate FET, and because the physical structure of this device emphasizing of the fact that the basically the gate electrode is the electrical insulated from the device body by the oxide layer. So because of this high insulation, IGFET has a high input impedance, because this eliminate any possibility of the feedback from the output to the input. So I will discuss here basically that is the basically the switching diagram of this, where we showed the gate, source and drain, and between the gate and source we have applied the gate to source voltage, and between the drain and source we have applied the drain and source voltage. So basically I will discuss then when we applied these both voltages, so the drain current basically is the function of basically VGS and VDS both. So for this process starting, I have shown here the drain current is function of both VGS minus VT and also the VDS drain to source voltage. So here I will discuss basically the normal diagram by which we have discussed the three steps of the basic steps. So I will adopt here in the MOS structure on applied of the gate to source voltage, and finally for the conduction of current I will provide the drain to source voltage, by which we have drawn the characteristics between the drain and source and drain to drain current at the constant VGS voltage. So that is the this is shown here the basically the normal gate structure, where we have upper layer is the gate, and between and between substrate and gate material here exists and gate oxide layer, silicon dioxide layer, and below that we have used the silicon surface of p type of substrate. So in I will show here the we have used here the p type of substrate which is used for the NMOS transistors, heavily doped N plus and N plus source and drain regions, and in making that we have access the channel for conduction of the current. So basically when gate voltage is negative, will be shown here in this diagram, when no electrons attracted towards the gate or between the drain and source. So majority carriers of the p-type substrate basically are the holes present between the source and drain. Those concentration increases underneath the gate between the drain and source. That is called the accumulation process. But there is no current is exists between the drain and source, which is flow between them, because we have applied here the negative voltage towards the gate terminal, and in basically the p type of substrate where majority carriers are the holes, we have basically the positive charge, and towards the negative voltage of the gate it is attracted between the source and drain, and that is the accumulation of charge between the source and drain underneath of the gate. But due to these charges, presence of these charges, when we have not applied here the drain to source voltage and only from VGS voltage, there is exists no current between the drain and source of this channel. And when basically when the gate to source voltage is 0, then no current is flow between the source and drain, then it is shows by the flat bed voltage when we get to source voltage is 0. But when we apply in next step, that is our VGS is our positive voltage, and VGS, and we will give the VGS voltage is greater than when up to threshold voltage. I will explain here that basically the when we applied this particular voltage positive voltage in a small positive voltage basically at the gate terminal. So it produces electric field which has the direction from the gate to substrate and perpendicular to the channel. So in this diagram I will show here when we applied the positive voltage on it. So under that condition basically we have applied here, the electric field basically exerts a force on the holes and push away from the oxide layer, and this electric field exerts a force over the electrons in upward direction, and this creates a depletion region in the semiconductor near the surface consisting mainly of the negative charge acceptor ions. So is this region called depletion region? Because it is depleted of the free electrons and holes. The holes have been forced away while the electrons have been absorbed by the boron dopant atoms. The depth of the depletion layer basically increases with the applied of this gate to source voltage. So this situation defines the depletion mode of the operation in MOS system, and the depleted MOS structure cannot support the flow of the electric current. So in this diagram I will show here, if we increase the gate voltage to a special value that is called the threshold voltage, then a change is observed in the charge properties. The value of the VGS at which a sufficient number of mobile electrons accumulate in the channel region to form a conducting channel is called the threshold voltage. So when we increase the gate voltage, more the electrons are exist in the between the drain and source for at a particular threshold voltage, and sufficient number of electrons are present accumulate there near the surface of the substrate underneath the gate, and that is basically the shown the conduction region between the source and drain. Basically the channel is created by the inverting of the substrate surface from p type to n type. Basically here I will shown in this diagram, when we produce a sufficient gate to source voltage over the threshold voltage. So basically underneath the gate between the drain and source, where we have access the majority carriers are the holes that has the positive charge on there, and when we increase the gate to source voltage, then depleted of the charges are there and accumulate the basically the negative charges, electrons accumulate on that. So basically positive charge p type to convert the n type, positive is convert to negative, means p type to convert in n type. So inversion layer is created basically. So now if a voltage is applied between the drain and source, current flow through this induced n regions carried by the mobile electrons. MOS device is in the conduction mode basically. So in complete process basically it is very clear that the gate voltage applied only to form the channel. So that is called the controlling voltage, and value of the current flow between the source and drain depends upon the drain to source voltage. So basically I will draw here the basically the drain current is the function of both VGS and VDS. When we provide the gate to source voltage more than the threshold voltage, channel is exist between the drain and source, but rather than current doesn't flow between the drain and source. When we applied the drain to source voltage, then when we increase the drain voltage, drain current is increases at a particular gate to source voltage. And suppose when we increase this particular gate to source voltage to another value, then at a less value of VDS we have increased the more drain current towards it. So that is the basically the phenomena of this process. So I will discuss here the basically the working of this enhancement mode of MOSFET. In this basically I will show here the diagram where we use the heavily doped source and drain regions, and underneath the gate basically there exists a channel, conducting channel between them, and shows here the dotted lines by which we have shows the depletion layer on p type of substrate. So in this basically where we have applied the positive voltage over the gate, over the threshold voltage, that VGS is greater than VT, and the same time when VDS is equal to 0. So basically channel is exist but no current is flowed between them. But when we applied the positive voltage and again at the same time we have applied the drain to source voltage basically more than the 0 voltage. So in this condition basically VDS is increased and the potential drop across the channel reduces the voltage between the gate and inversion layer near the drain terminal. So thus the voltage between the gate end point along the channel decreases from VGS and at the source end to the VGS minus VDS at the drain end, since the channel depth depends on this voltage basically, because we find the channel is no longer of uniform depth. In previous in 4.68, here the channel is in uniformly distributed between the source and drain. But when we apply the drain voltage more than the 0 voltage, then the basically the channel is tapered. The channel length, channel width is basically more towards the source, and it is basically the deepest at the drain terminal. So basically channel is tapered. It is basically the deepest at the source end and the shallowest at the drain end. So because VDS is when we increase the VDS is further increases, then channel becomes more tapered and resistance basically according to it. That is called the linear region operation, or in non-saturated region basically. So in this region we have used the VGS is minus VTS is greater than VDS, that is called the non-saturated region, where we use it is worked as a linear region. When we increase the drain to source voltage, drain current is linearly increased at a particular gate to source voltage. So when we increase the VDS voltage at a particular more than this value, so in this case basically the channel depth at the drain end becomes equal to 0, and the channel is said to be pinched off. So gate is isolated from the conducting channel by this depletion region at the drain end. When we increase the VDS value at a particular level, so increase the VDS beyond this value has little effect on this channel and the shape, and the current through the channel is remains constant. Thus when we increase the drain current will when saturate to a constant value, because when we increase the VDS value at a particular value, then drain current is constant and the MOS is entered saturated region of operation. So as increase in VDS above the saturation value will cause a pinch off point P move towards the source at the drain end. That is shows in this diagram, where we use the VDS increase at a particular level. Channel basically the pinch off point is shifted from the towards the source end. That is shows by L dash. So that is the gap we have shown here between the L and L dash. The basically the pinch off point is shifted towards the source end when we giving the VDS at a more than a particular value. So basically we have shown here the two types. Basically when the VGS is less than the threshold voltage, no channel layer exists. The two regions are physically separated each other, no direct current flow between the drain and source, and that is basically the open circuit exit between the drain and source terminals, which is drain current is 0. That is called the cutoff region of operation. But in another hand, when the gate voltage increases, VGS is greater than VT, then saturation current or gate oxide and channel is created between the drain and source, and basically that is basically flow the current between the drain and source from existence to the channel. That is called the active mode of operation. So in active mode of operation, when we applied a constant gate voltage and vary the drain to source voltage, then increase the VDS, drain current increases linearly at a constant gate to voltage, that is called the linear region. When we further increment of the drain to source voltage, then current does not continues with IDS VDS relations are does not basically continues at a straight line, and that is basically the band. So and entered in the saturation region. So in the saturation region, basically the drain current is saturated and does not depend on the drain to source voltage, that is called the saturation region. Here I will show in this diagram, where with the gate voltage is now increases at a particular value. Here I will shows here the before the pinch off, when VDS increases, drain current is continuous increases, that is called the non-saturated region, where VGS is VT is greater than VDS, and after the pinch off region where VGS mid is greater than VDS, under the condition after the saturation region it is entered in the saturation region, and when we increase the drain current, when we increase the drain to source voltage, and drain current is not increasing according to it, because it is in the constant region, or basically it is in saturated region after the pinch off. But when we take the gate to source voltage at a particular different level, then it will cause an increase in the inversion layer charge. So channel resistance reduces, causing a large drain current at a particular value of VDS. So the pinch off point basically will now occur at a higher value of the VDS. So basically these are the relationship between the ID and VDS according to the particular value of the VGS. It is the for N channel type of MOSFETs, and below that I will shown here in the diagram, that is for the P channel type of MOSFETs, where the minus VDS and minus IDS relation show up here, non-saturated regions at a particular value of minus VGS1, VGS2, VGS3 and VGS3 before the pinch off, that is called the non-saturated region, after the pinch off, that is called the saturation region. So these are the basically the curves by which we shows the electrical connections by which drove the electrical parameters. These are the VDS and IDS at a particular VGS value. So these are shows the electrical connections or electrical relationships between the drain and voltage by these characteristics. Thank you.